Hello, Matt here from chemistrystudent.com. In this video, we're going to look at SN1 and SN2 mechanisms, based on the nucleophilic substitution of primary and tertiary halogenoalkanes with hydroxide ions. We're going to talk about what those letters and numbers mean, why reactions may happen via SN1 and SN2 pathways, and how we can use reaction rate data to predict whether a reaction is occurring via an SN1 or an SN2 mechanism. Nucleophilic substitution reactions of halogenoalkanes have been covered in separate videos. Check the links in the description below. Before we talk in detail about the mechanisms, there are a few essential ideas you need to be comfortable with. A nucleophile is an electron pair donor that is attracted to a positively charged or electron deficient atom. Nucleophiles can be negatively charged and always have a lone pair of electrons. A substitution reaction is where one group or atom in a molecule is swapped for another group. In organic chemistry, we show the possible steps occurring in a reaction by using mechanisms. Curly arrows are used to show how a pair of electrons move as bonds get broken and formed. The arrowheads always point towards where the electron pair is moving to. Primary halogenoalkanes have a halogen bonded to a carbon atom that is bonded to only one other carbon atom. Secondary halogenoalkanes have a halogen bonded to a carbon atom that is bonded to two other carbon atoms. Tertiary halogenoalkanes have a halogen bonded to a carbon atom that is bonded to three other carbon atoms. Apart from with iodine, the carbon-halogen bond in a halogenoalkane is polar due to the halogen's high electronegativity and carbon's lower electronegativity. This means the halogen pulls the electrons in the bond towards itself slightly and as a result has a partial negative charge, and the carbon that it is bonded to has a partial positive charge. Rate equations are based on the slowest step in a reaction, called the rate determining step, and show how the concentrations of reactants involved in this rate determining step influence the rate of the reaction. Recap done? Let's go! Halogenoalkanes, also called haloalkanes, react with hydroxide ions in aqueous conditions to form alcohols. There are actually two mechanisms by which this reaction can occur, depending on the type of halogenoalkane reacting. Primary halogenoalkanes follow what's called an SN2 mechanism pathway, and tertiary halogenoalkanes an SN1 mechanism pathway. Just to be awkward, secondary halogenoalkanes can sometimes follow both. So let's first have a look at a primary halogenoalkane reacting with hydroxide ions. A negatively charged hydroxide ion, OH-, acts as a nucleophile and will attack the partially positive carbon atom from the carbon-halogen bond in the halogenoalkane. As a hydroxide ion comes near this carbon atom, the lone pair of electrons from the oxygen in the ion are used to form a new bond between itself and the carbon. At the same time, the carbon-halogen bond will start to break, with the halogen atom taking both of the bonded electrons with it, ultimately becoming a negatively charged halide ion. This creates an alcohol, more specifically a primary alcohol, as the hydroxy, OH group, is at the end of the carbon chain, just like the halogen group was in the original primary halogenoalkane. For a very short period of time, there will be a transition state in which the hydroxide ion is bonding to the carbon, whilst at the same time the carbon-halogen bond is breaking. Both the hydroxy group and the halogen will be attached to the carbon. This transition state could never be isolated. It's more of a theoretical structure that we predict must form. If you were to track the energy of the halogenoalkane molecule as it reacts in this way, you would see its energy increase as the hydroxide ion comes near it and the carbon-halogen bond starts to break, before it then decreases again as the necessary bonds get made. That very top part of the energy curve represents the transition state of the mechanism. A bit like imagining a ball being thrown up in the air. For an incredibly short period of time, the ball must be stationary as it stops going up before it starts to fall back down. Of course, it doesn't just stay there, just like the transition state in a reaction doesn't exist for very long at all. This mechanism is relatively straightforward and all happens in one step. Nucleophile comes in and carbon-halogen bond breaks. The reaction occurring is a substitution. The hydroxy OH group is substituted for a halogen group, and it is a nucleophile that is causing the reaction and being substituted. This is why it is called a nucleophilic substitution, often shortened to SN, S for substitution, N for nucleophilic. The single step in this reaction needs both the halogenoalkane and nucleophile, two reagents or bimolecular. We show this with the number 2, and the whole mechanism can be summarized by SN2. The rate of any reaction is based on the concentrations of reactants involved in its slowest step, the rate determining step. As there is only one step in this mechanism, this has to be the rate determining step. Because of this, the rate of SN2 reactions is based on the concentration of the molecule undergoing a substitution and the nucleophile reacting. This gives the rate equation, rate equals rate constant K multiplied by the concentration of halogenoalkane multiplied by the concentration of nucleophile, in our example, hydroxide ions. Changing the concentrations of either of these reactants directly changes the rate of the reaction. Hopefully straightforward so far. Now let's have a look at a tertiary halogenoalkane reacting with hydroxide ions. In the same way as before, OH- is going to act as a nucleophile as the oxygen has that lone pair of electrons, and it's going to be attracted to the partially positive carbon in the carbon-halogen bond. The problem now, though, is the hydroxide ion is unable to get close enough to the carbon atom to form a bond with it whilst the carbon-halogen bond breaks. This is because the carbon groups around the partially positive carbon are much bigger than the hydrogens surrounding the carbon in a primary halogenoalkane and effectively block the hydroxide ion from getting close enough to attack the partially positive carbon. We call this steric hindrance. If the hydroxide ion is going to bond with that carbon, the carbon-halogen bond will have to completely break first, forming a carbocation that the hydroxide ion can easily bond to. A carbocation is an ion that has a carbon with a positive charge in. It is formed as an unstable intermediate in a reaction. This is the key and fundamental difference to the mechanism with a primary halogenoalkane. In that case, the SN2 mechanism, the carbon nucleophile bond formed at the same time as the carbon-halogen bond broke. However, with a tertiary halogenoalkane, the carbon-halogen bond has to break before the carbon nucleophile bond can form. This means there are two steps in the mechanism. First, carbon-halogen bond breaks, leaving a carbocation intermediate. Second, the nucleophile, hydroxide ion here, forms a bond with the carbon that has a positive charge in the carbocation intermediate. A tertiary alcohol is formed and a halide ion is released. The carbocation intermediate that gets formed is more stable than the transition state in the SN2 mechanism, and, although hard to isolate, does actually form for a short period of time. Meaning, if you were to track the energy of the halogenoalkane as it reacts, its energy would increase as the carbon-halogen bond breaks, before then dropping a bit as the carbocation intermediate forms, before then increasing again as the hydroxide ion comes near it, and then dropping as the new bond gets formed. This gives an energy profile diagram that looks a little bit more complicated than for the SN2 mechanism. Two little hills with a slight dip in the middle. That dip is the carbocation intermediate, and the two hills show us that two steps are occurring in the mechanism. Just like with the SN2 mechanism, the reaction occurring is a substitution. The hydroxy, OH group, is substituted for a halogen group, and it is a nucleophile that is being substituted. nucleophilic substitution, or again, SN. S for substitution, N for nucleophilic. This time, however, only one reagent is needed in the first step to start the reaction. The slowest step, rate determining step, is this first step, the carbon-halogen bond breaking. This means the rate of reaction is only dependent on the concentration of halogenoalkane reacting. It is only based on one reactant and is called unimolecular. We show this with the number 1, and the whole mechanism can be summarized by SN1. The rate equation would be rate equals rate constant K multiplied by the concentration of halogenoalkane. From this, we can see that changing the concentration of nucleophile, hydroxide ions for these examples, has no impact on the rate of an SN1 reaction. We can use reaction rate data to predict whether a substitution reaction is occurring via an SN1 or SN2 pathway. This is because both mechanisms have different rate equations. Changing the concentration of either the halogenoalkane or hydroxide ion will affect the rate if an SN2 mechanism is occurring, as the rate equation involves both of these reactants, and the value for rate will change if either of these concentrations change. For an SN1 mechanism, only changing the concentration of halogenoalkanes affects the rate of the reaction. This is because the first step in the mechanism, the breaking of the carbon-halogen bond, is the slowest rate-determining step and only involves the halogenoalkane. It makes no difference how much nucleophile is present, the reaction can only go as fast as the carbon-halogen bond breaks. So, to summarize, SN1 and SN2 mechanisms are two different pathways that can occur for nucleophilic substitution. The S stands for substitution and the N for nucleophilic. The number 1 in SN1 means only one reactant is involved in the rate determining step of the mechanism, and it is described as being unimolecular. The number 2 in SN2 means two reactants are involved in the rate determining step of the mechanism, and it is described as being bimolecular. Usually, primary halogenoalkanes react by SN2 mechanisms, and tertiary halogenoalkanes react by SN1 mechanisms. Secondary halogenoalkanes can sometimes react by both. The SN2 mechanism occurs in one step. Nucleophile bonds to the partially positive carbon as the carbon-halogen bond breaks, and there is a momentary transition state in the middle where both groups are attached to the carbon. The energy profile diagram for an SN2 reaction shows one peak. This is where the transition state is. Tertiary halogenoalkanes are unable to react by SN2 mechanisms due to steric hindrance. Incoming nucleophiles are unable to get close enough to attack the partially positive carbon in the halogenoalkane, as they are blocked by the free carbon groups bonded to it. Instead, the carbon-halogen bond has to break first, forcing an SN1 mechanism to follow. An SN1 mechanism occurs in two steps, and an intermediate gets formed in the middle of the reaction. The carbon-halogen bond in the halogenoalkane breaks, forming a carbocation intermediate, and then the nucleophile bonds to the positively charged carbon in this intermediate. The energy profile diagram shows two peaks, one for each step, and a slight dip in the middle. This dip is a carbocation intermediate. To help remember at this level, think SN1 equals 2 steps, SN2 equals 1 step. For SN1 reactions, the rate of reaction is only based on the concentration of the molecule that is going to undergo substitution. In our examples, the halogenoalkane. This gives a rate equation of rate equals rate constant K multiplied by the concentration of halogenoalkane. Changing the concentration of the nucleophile has no impact on the rate of reaction. For SN2 reactions, the rate of reaction is based on the concentration of both the molecule that is going to undergo substitution and the nucleophile reacting with it. This gives a rate equation of rate equals rate constant K multiplied by the concentration of the halogenoalkane multiplied by the concentration of the nucleophile. Changing the concentration of either the halogenoalkane reacting or the nucleophile will affect the rate of the reaction. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.